So we're going to continue the discussion on bevel gear today, and we will, based on the progress we made with the other section, we kind of went through half of the problem for the helical gear. So let's get to it without any delay. If you recall from, just to go over this in a few minutes, just to remind you, we have this problem. We have a pinion and we have a gear. These are the bearings, and we are interested to know what are the forces acting on the bearings for the gear, not for the pinion, knowing that one of them is going to handle the thrust load. Okay. Now, what we have been told is that this pinion rotates at an RPM of 600 revolution per minute. It transmits 5 horsepower to the gear, and all the dimensions are given to us. So what I want to tell you is that when we know the either the torque or the power, we can find the transmitted load. Okay, like here it is basically this distance. The torque divided by this distance is going to give us the transmitted load. However, we also told you that once you know the transmitted load, you will be able to find the radial and the axial loads by knowing the pressure angle as well as the angle gamma, which is like the cone angle kind of. So what you should know is that this is small gamma is for the pinion. If you use capital gamma in the same equation, you will find the forces acting on the gear. This is what we are going to do in the next problem. So what should we do over here? We said, okay, we'll draw the free body diagram, right? Knowing that the two gears mate over there, and we have the radial force, the tangential force, as well as the axial force. Cool, acting on the gear. And here we have bearing C and bearing D. In the problem, it was said to us that bearing C is going to handle the thrust. And that's why it is taking the axial load. The other bearings only have radial loads acting on it. And we have, of course, the dimension. And we know that this power is going to generate a torque there. So that's the torque. Now, so if we go back to the dimensions over here, we will see that, let me clean this up. We'll see that the gamma angle for the pinion, look at it. It's over there. This is gamma. It's coming up. Yeah. All right. That's gamma. And then along the line over here, we have, this is capital gamma. So this is the gamma for the gear, and the other one is gamma for the pinion. Of course, they both add up to 90, and knowing the dimensions for each one will let you, the adjacent and the opposite, or the hypotenuse, whatever, through the symbol triangle, right triangle, you will be able to find these angles, which is here. This is a small gamma. It is 3/9, the inverse tangent of a 3/9, which is 18.4. You can take the inverse of that, which is 9 over 3, or you can just say 90 minus 18.4, which is 71.6. So this is not a big deal. You know the angle right now. Now, if you know the angle, okay, you would need to know the velocity. Why? Because if we want to know what is the transmitted load, this is in pound for force and feet and minutes. So what do? We have 33,000 multiplied by the horsepower, which is 5, and divided by the pitch line velocity. Now, the pitch line velocity, or the pitch radius velocity, is 2 by, that's a constant, multiplied by the radius of the pitch line, or the pitch radius, multiplied by the RPM, which is 600, divided by 12. Now, what is RP? Okay, RP is over there. So this is just for you to know. This is RP. So basically, it is the distance, okay? It is the distance from the center over there, where the two cones are going to meet, to what is supposed to be an average line. It's just like we know that we have to, in reality, the gear is like this, and the point of contact is somewhere here. So this is why they call it average. It's just like probably taken at the middle as an assumption. So it is called the average. You put all of these numbers, you get the velocity. If you plug in the velocity, you got WT. Look, whenever we have the transmitted load in gears, you are usually set for the rest, because there are always relations. Like this is WT tan phi, the pressure angle, multiplied by cosine capital gamma. This is WT tan phi multiplied by sine capital gamma. If you got those forces, both of them, this is 46.6 pound feet, and this is 140. 140 is WA, it's the axial load. And if you look around, this axial load has no resistance, okay, except this one. So that reaction, okay, is actually the basically WA. That axial reaction is WA. So now what do we want to do? When we know these forces, this is where the important question comes. Now, if you look in here, we have WR, WA, and WT. All of them are known. Now, if you look, these are acting along the X, Y, and Z direction. And if you were to take the resultant and find their angle, you will end up with a resultant force like this, which is called W, oriented in three-dimensional plane, okay? Three-dimensional. And in here, we have two radial loads acting along the radius, because if you imagine that there is a bearing over there, along that radius from all directions, we have two forces, and then one which is axial over there. So in reality, even this force can be envisioned as a three-dimensional force, one resultant force, oriented at three different angles with respect to X and Y and Z. Yeah. And of course, this one is going to be two-dimensional because there's no third one, but it is going to be somewhere a resultant force acting within the plane of Y and of Z and X. Okay. And why I'm telling you this is because you have two ways here to deal with this problem. What we were asked for is to find the reactions at the bearing locations for the gear. So you basically need to determine this is unknown, this one is unknown, this one is unknown, this one is unknown, and this one is unknown. Now, just to be consistent with what I just said, we understand that there is no argument that WA is the same as FC, and FC is the same as WA with, FCY. There's no doubt about that. You will see it later. But the other reactions are definitely unknown. So you have two choices. Either to say, I have a very nice three-dimensional mind that can figure out how these forces are going to interact with each other. In another word, what you need to do is just the regular business, summation of forces along X, summation of forces along Y, summation of forces along Z, summation of moment about D, about C. You need to do all the equilibrium equations to find these reactions. The question is this: when you sum up the forces, it is not difficult, but when you sum up the moment, it's also not difficult, but there is a good chance you may forget one force, or you forget that, that force make a moment about Y, and or it actually make a moment about Z, and the other one make a moment about Y, and so on. So you may forget one force, and then you fall into trouble. And that's why in this problem, what I like is that the solution is trying to teach you how to use the vector notation, basically. You've been probably studying this for too long. I don't know if you ever encounter a problem which will convince you 100% how useful is the vector notation. I can't. It's very, very handy here. Very nice. So let me see what are we going to do. So what are we going to do? We want to take the summation of the moment about point D. Okay? Now, we know from a previous knowledge that the summation of moment in a vector notation is the position vector R cross the force, which is equals to 0. Yeah. So what are we going to do? We will extend a position vector between point G, this is point G, by the way, and this is point D, and we will extend another position vector between G, D, and C. And then we will cross the position vector with the forces in here and in there. So let me show you how. One by one. Let's talk about the position vector, which is being extended from point D to point G. Okay? Now imagine that somebody told you you want to go from point D to G, and the only way is to go through the axis, like x-axis, y-axis, and z-axis. Imagine that these axes are the street, and anything in between full of buildings. If you want to go from D to G, you cannot just cross the walls and buildings and houses and stores. So what should you do? Well, a reasonable way to say is, I am going to go from point D to here. This is one tiny little vector. And then I will have another vector, which is like that. Isn't that true, ya Shabab?
Yeah.
Yeah. So all what I need to do now is to recognize that this one is a positive I vector, and this one is a negative J vector. Yeah, do you appreciate that? So this is a negative J because positive is in this side and positive Z is in this side and positive X is in this side. So if I do so, I will look at this. This is a 3.88 I, and that there it is. And then I have a negative J vector. This negative J vector is composed of two distances. The first one is 2.5, and the second one is been hidden by the marker. So the second one is 1.293. So what do? I put the minus sign, and I have 2.5 plus 1.293 J. I add them together, and there you go. This is the position vector. This one now is this. It is the combination of the green and yellow. What should I do? I should now clean this and make it probably in green. So the other vector is this vector. All right, which is basically a negative J vector composed of this distance and this distance. So you add these two distances over here, and you got a negative J vector. Now, what should we do? Is this. You go and take the red vector, this one, the red one is there, and you multiply it cross by the W vector. Now, the W vector itself is composed of three tiny vectors, one along X, one along Z, one along Y. Yeah? So, and that's what we did. So look, we took this guy over here, and then we put the cross just to indicate that this is a cross product. And then look carefully. This WT is positive, and it is going toward the Z direction. There it is, positive K. The other one is WR, which is negative I. There it is, negative I. The other one is negative J, and there it is. Now, what is nice about this? I mean, you can imagine when you cross them, you know that you will use the convention I cross I by J, you get K, positive. You cross J by K, you get I. You cross K by J, you get J. So if you do the reverse, it is negative. But I should also remind you, this is a trivial, that if you cross the same product, the same unit vector, you get a 0. And that's where the vectors become helpful. You don't need to worry. There are some forces that will not make a moment, and they will cancel out just by themselves, because you will have I by I or J by J or K by K. You get that? And it will become 0. So you actually don't need to worry about the magnitude. You don't need to worry about the direction. You solve both of them at the same time in one single equation. Now, the second one is the position vector RC, which is the green guy over there. There it is, crossed by FC. FC is also a vector which is composed of 3 components. One of them is I, one of them is J, and one of them is K. Now, one more. We are summing all moments about point D. So, which means we will add all sort of moments about point D, including the torque. The torque, if you use your right-hand rule, torque here is TJ. We don't know its magnitude, but we know that it is certainly going toward the J positive direction. Good. Of course, what did we do? We substituted all of the forces with variables fcx, fcy, and fcz. They are unknown. Okay, so and t is also unknown. Now, if you recall, okay, from dynamics, for example, if you have this vector plus this vector and a little tiny one, which is all summed to be zero, it means here you can actually, from this vector equation, you can withdraw three scalar equations. And you say, for example, just for example, for J component, what do we have? We have a minus 1575, and then in here we don't have J, but there we have one J, which is T, so plus T, which is equal to 0. All of the J components are equals to 0. The J component on the left-hand side equals to 0. The I component on the left-hand side equals to 0. And the K component on the left-hand side also equals to 0. So clearly from this, you will get T equals to 1575, which is pound force inch. And then you continue, and you will see that you will be able to find FCZ, FCX as well. FCY was cancelled out. Okay, that's fine. That's fine. It's okay. If we now imagine that this is now known, this is known, and in reality, this is the same as this one. So this is kind of known. You are left with these two guys, right? So what is the next step? Is to take the sum of all forces, which is equals to 0. So if you sum all of the forces of the whole system and say that this is equals to 0, you will have the forces at point D plus the forces at point C plus the forces at W. All of them is equals to 0. So what are you going to do? You're going to substitute them with their corresponding value. The vector W is entirely known. The vector for C is known except this one, which we know it is equals to the axial load. And these two are completely unknown. So what should you do? You know, as I said, that if C is equal to 140, so if you know that, you will end up with solving the other equation, you will end up knowing exactly what are all the forces and their directions acting at point C and also point D. Yeah. Now, if you want to design for a bearing, selection, whatever, you know the forces that are acting exactly at each bearing. Okay. Now, what are we going to do? We are going to move to helical. I think by just, you know, the first new thing it's probably to you is probably this bevel gear. And now you will see helical gear. Things are not very much different. And in the end, the next class, we'll talk about worm gear, which are also not going to be different. So these are three. Now taught you how to handle a gear problem with three-dimensional forces. Spur gear was something that we did kind of, even in 307. So this is a helical gear. Before we start with the force analysis of helical gear, I need to bring you back to a few items or a few issues that I said. Probably the time wasn't ready, you know, wasn't the best to discuss them, which is the right-handed, left-handed gear. So what is the story? The idea here is that helical gear, as you see, has this teeth which are cut within helix angle. And of course, the force is going to push at a certain pressure angle. Now, we know that there are two kinds of pressure angles. The first one is along the normal. The second one is along the transverse. Okay? Now, also, we know that this angle psi is what is known as the helix angle. This is the angle by which the teeth are cut with an inclination. Now, definitely, at a three-dimensional space, this resultant force is coming and hitting the gear tooth at one single point. And by knowing these angles, one with respect to the normal, one with respect to the transverse, and the other one within the plane where the helix angle is, we can project this resultant force to find an axial force, a radial force, and that transmitted load, which is a tangential force. Okay? Now, we want to have an understanding about the convention of, how to know these forces, their direction, and so on. So the first thing that you should, regardless of the fact that you were asked to analyze the gear or the pinion, regardless, the radial force is the easiest of all. It is always acting inward. What does inward mean? It means if this is the gear, the inside of the gear is the inward direction. So it is always pointing toward the center of the gear. So if you have a gear, you will not have a radial force which is popping out of the gear. No, it will always act on it. Okay, inward. So this is something we know. Good. So it is always inward. The question is, what is the direction of the transmitted load? The transmitted load, this guy, okay, or the tangential component, is always acting opposite to the rotation. So if this gear rotates in this direction, just put that opposite to it. Why? It's common sense. If it rotates this way, the other gear will rotate in the opposite direction, and this transmitted load will not be there unless you have something, engaged with the gear. And so it will only come when you have the other gear opposing the gear that we are talking about. Whether it is, let's say the driver, then the driven is opposing it, so it's going in the opposite direction. So it's always acting in the opposite sense of the rotation. The rest is now this axial one. Okay, so for the axial one, we need to go back to this. I promised you that we're going to go back to this rotation of the helix of the helical gear. And it is written here that the same convention is used for worm gear. But the first thing first, there is a right-hand helical gear and there is a left-hand helical gear. And as simple as you see in the slide, the right-hand helical gear is the gear which, if you put your right hand on it, your thumb will point in the direction of the teeth. So the teeth are there and your thumb is just aligned with them. This is a right hand helix gear. The left hand is very, easy now, right? Just put the left palm of your hand and then your thumb is going to point toward the direction of the teeth. Understood? That's a simple lesson, right? Now, what you should understand is that this A and this is B. So these are not four cases, these are two, one case and another. But in the first one, we're looking at different views. So this is like you are looking into this view and over here. So you're looking at this view in this one. But what is this for? Let me show you. It says down that this is a right hand. What does that mean? It means that we are looking at the driver when it is a right hand. So if you put your palm, you will see that the palm, this is the thumb, and it is, yeah, it is the right hand. And this one also a right hand. You see that? Both of them. Okay, so we are focusing on the driver, and it is right hand in both A and B. Okay, good. Now, the second thing is this. If the gear is right hand, okay, then how do you determine where is the thrust? How? Well, first, if it is right hand, you raise your right hand. The second thing is now to move your hand in the direction of the motion. So if you look at this one, if you look at this one, okay, the arrow of the rotation is down. So the only way I can simulate this with my right hand is to do like this. That's the rotation of the gear. And now, where is my thumb? Going this way. This way is the direction of the thrust. And that's why in the opposite way, so the thrust is going this way. So where do we put the bearing, ya shabab? The thrust bearing on the opposite side. There it is. You see? Now look at the other one. Now the rotation is up. Up with the right hand means I need to rotate this way. So the thumb is acting this way, which means the thrust load is going to act this way. And that's why I should put the thrust bearing on the opposite side. You got that? You can do the same analogy, okay, with the one which is left hand. Now, so let's go back over here. So what are we going to do is this. If you look over here, ya shabab, what do we have? We have a this example. Let me clean this up for here. Okay, so if we know what is the result, which is, by the way, yeah, less likely. Okay, less likely. But if you know it, this is the total force, then you multiply the total force by sine phi n, the normal pressure angle, and you get the radial force. If you multiply it by cosine phi n, cosine psi, you will get the tangential component. If you multiply it by cosine phi n, by sine psi, you will get W, which is the axial force. However, we know that most of the time, W is usually known. At least if it is not given, we know the power, we know the RPM, we can find the velocity. From the velocity and the power, we can get WT, and from WT, what you need to do is to find WR and WA, as well as the resultant. So if you know WT, then you can simply multiply WT by tan phi T. This is the transverse pressure angle, and this one, WT, multiplied by tan psi, which is the helix angle. Okay, if you want to find the resultant, then this is the equation. Understood? So what are we going to do next? Is that we have here another problem, just almost identical to the other one. The only thing is that, you know, the nomenclature, we have different parameters, different angles, because this is a helix gear. So what do we have over here? We have a motor. This is a motor. Okay, and the motor is sitting, we have here its shaft sitting on two bearings. One of them is actually bearing A, which is going to take care of the thrust. Now, the thrust is to the left, right? So does it make sense? Well, let's look. You have
Oh, doctor, we can't hear you.
It's mute.
Doctor, we can't hear you. I think you're muted.
okay. Sorry, Shab got disconnected. So what I was saying that the helical gear is a right hand. Why? Because in the problem, you were not told about this, but you can see the angle of the head, right? And you can just comfortably put your right hand, and you'll see that your thumb is pointing toward the left direction. So one of these key bearings must take care of that thrust. Otherwise, this thrust will damage the internal mechanism within the motor. So we know how many teeth are there on this helical gear, and what we also know is that this is rotating at an RPM of 1,800 revolution per minute. We have and transmitting 1 horsepower, okay, in the clockwise direction as viewed. What do we know is that look, I want you to be very careful with this. It says here that we are having, okay, so we're having a normal pressure angle of 20 degrees and a helix angle of 30 degrees. You see that? And we have been given a normal diametral pitch. This normal diametral pitch is P capital N. And I know you probably forget those equations or these parameters, which is equal to the 12 teeth divided by inches for each inch. Now, what do we want to know again is that this bearing A is taking the thrust. And we would like to know also what are the forces acting on the pinion side here, bearing A and B, knowing that A is taking the thrust load. Now, what I want you to remember, okay, is that the relation that we stated before about the helical gear, you probably forget them. So let me try to remind you. We have a relation which says that the cosine psi, which is the cosine of the helix angle, is equal to the tangent of the normal pressure angle divided by the transverse pressure angle, by the tan of the transverse pressure angle. So what we were given is this and this. Now, just because we were given two, it doesn't mean we need to find the third one unless we need it. And if I want to pull you back, okay, your target, ultimate target is to do this. Now the horsepower is given, it is 1. What you don't know is the velocity. So what is the velocity? The velocity is equal to by a constant divided by 12, another constant, multiplied by n, which is 1,800 RB revolution per minute. We are fine. The only thing which is unknown is the diameter. Now this is the pitch diameter. Now the pitch diameter for a helical gear, look at it. It is equal to the number of teeth, which is 18. I'm talking about the pinion, huh? We said we want to analyze the pinion, so we should stick there. Divided by the what? This PT is the transverse diametral pitch. The transverse diametral pitch. Just like the pressure angle, we have one along the normal, one along the transverse direction. The diametral pitch, we have it along the normal and the transverse. Now, so I need to find D. To find D, I need to find PT. To find PT, I can use this equation. Why? Because Pn is given to me, and cosine psi, I know it, and that's how I find PT. You get that?
Yeah.
I would like to remind you that the normal circular pitch over there is different than this one. And I remember I talked to you about this, that be careful, this is small letter, this is capital letter. So we are not going to use this. I'm bringing it here to remind you that it is not what we need. Okay, so what are we going to do? We are going to find...
you said the module, I remember you stating something about the module being equivalent to the diametral pitch, but in the British system?
Yes.
Okay.
Yes. So what do it is? Yes, it is equals to the diametral pitch. So what happened is here. We are going to go using this equation. We're going to multiply this by this. We are going to, here. We are going to take this up and take this down, and then take the inverse tangent. This is 20, this is 30. We found the transverse pressure angle. When we find that transverse pressure angle, okay, we will then, ya shabab, find PT, okay, and the PT is equals to Pn, which is 12. This is what was given to us in the beginning, multiplied by cosine 30. Now, then what do we have? We get the value here, which is 10.39 teeth per inch. We take this, the number of teeth n over there, we divide it by PT, and we get the pitch diameter. When we find the pitch diameter, we can use it to find the pitch line velocity. And when we find the pitch line velocity, we plug it in there to find WT. Now, if you recall, once you know WT, you're done. That's it. You're done. Why? Because you can find WR, WA, and even W. We're not going to use W a lot, probably not. But if it was requested, it's fine. We probably will need WR and WA because these are the components that we are going to use in the summation of forces and the summation of moment. Now, you remember we found WT, sorry, phi T, the pressure angle along the transverse direction. We used its value by multiplying it by WT in order to get WR. This is done. Then we use WT multiplied by tan psi in order to find WA, which is the axial load. Now, just by looking, by inspection, ya shabab, you will see that this axial force, which is 23.3 pound force, has no resistance except the thrust over there. So this is already known. The idea is we need to find this, we need to find this, we need to find this, and we need to find this. And in the process, we will probably even find the top. Yeah. So I am going to stop in a second. So in the next class, I'm going to show you quickly, then we will move to worm gear. I'm going to show you that with clear thinking, especially, because this point is in the plane, You understand? It is in the same plane. You can probably handle the summation of the moment, everything, without the need of vector notation. But what is interesting about this problem is that the textbook provided us with the solution using both techniques, which is very, very nice. So you will see here that the solution is done using vectors, and in here using scale. Okay, we'll discuss this inshallah next class. I will stop now to take your attendance. So stop this.